All right, hello everyone. I have the top of the hour, so we are going to go ahead and get started for today. Um, Welcome back to the third day of the Flash Drought virtual workshop. Today is a jam-packed day, but also an exciting one because this is really when we get into the next steps and where we go from here. My name is Molly Wolozin, and I am one of the Regional Drought Information Coordinators with NIDIS, and I coordinate the Midwest Drought Early Warning System, and I'll be the moderator for today. Next slide, please. Just a quick review on the guidelines for the meeting. If you're not speaking, please mute your audio and turn off your video unless you are speaking to the entire group. You can turn on your video at that point if you would like. We are pretty active in the chat box, so please open up the chat box. You can expand it to make it larger by clicking on a little arrow above the chat box. I think it's a little bit different for Mac and PC, but hopefully you can find that. If you do have a question or comment to say during the group discussions or during the presentations, please use the chat box. If during the discussion you want to say something, you can type hand in the chat box and we'll put you in the queue to speak. If you do run into any technical issues, please reach out to Tammy. Her email and phone number is on the screen there if you have any questions. And Tammy, maybe if you wouldn't mind putting that in the chat box as well, just so we can keep it after we move on to the next slide. All right, next slide. Just a brief overview of today's schedule. Today is really focusing on the challenges and opportunities, gaps and needs when it comes to monitoring flash drought prediction and also planning and response. And after that, we will have more discussions on prioritizing and next steps. But today we're going to start out by looking at some presentations, talking about the challenges, opportunities, gaps, and needs. We'll go into our third and final breakout groups. And then after lunch, we'll have a report out and group discussion. And then finally, we'll end the day in the last hour. We'll be talking about revisiting the characteristics of flash drought, and then also doing a prioritization exercise to help us hone in on some next steps that we can take. Next slide. So to get us going here, as I mentioned, we're going to listen to some pre-recorded presentations. This one's a little bit different, where after each of these presentations, we are going to have just a few minutes for the speakers to live comment on some of the themes and topics that have come up throughout the previous 2 days. First up, we're going to hear about flash drought monitoring from Jason Otkin from the University of Wisconsin and Mark Svoda from the National Drought Mitigation Center. After that, we'll go to prediction. Andy Hoyle from NOAA's Physical Science Laboratory and Hylan Wong from the Climate Prediction Center will be talking to us about prediction. And then finally, Tim Hall from the Iowa DNR will be giving a presentation on planning and response to flash drought. So I think we can go ahead and move into the first presentation.
Hi, good morning, everyone. My name is Jason Otkin. I'm a research scientist at the University of Wisconsin-Madison. My co-author on this presentation is Mark Svoboda. He's the director of the National Drought Mitigation Center. In this talk, we're going to provide an overview of some of the tools that have been used to monitor flash drought and describe some of the strengths and weaknesses. This will then lead to a list of challenges, gaps, and needs that have to be addressed in order to effectively monitor flash drought across the United States. So I'm going to start out with a schematic that shows the typical evolution of flash drought from the perspective of vegetation impacts associated with agricultural and ecological drought. To capture the evolution of this type of flash drought, it's necessary to use a multivariate monitoring framework that includes a set of variables depicting anomalies in precipitation, evaporative demand, soil moisture, evapotranspiration, and vegetation health. The schematic shows how a multi-week period of elevated atmospheric demand, along with below normal precipitation, can lead to a series of cascading impacts at the land surface. Now, during the onset phase of a flash drought, soil moisture deficits tend to develop in the topsoil layer first, and then penetrate deeper into the soil column. Vegetation can greatly accelerate the depletion of root zone soil moisture due to enhanced evapotranspiration, or ET. Now, though ET may initially increase in response to the elevated evaporative demand, the vegetation will curtail its water usage as soil moisture continues to decrease, and this can then lead to a rapid decrease in ET. Now, once drought conditions become severe, visible signs of moisture stress, such as yellow or curled leaves, can become apparent in the vegetation. And a final point I want to make here is that this sequence of events has to happen rapidly for it to be considered a flash drought event. So to illustrate the importance of using multiple variables for flash drought monitoring, I'm now going to spend a few minutes providing an overview of some of the strengths and weaknesses of different classes of tools that have been used to monitor flash drought events. The first one I'm going to discuss is precipitation. Now, an obvious strength of precipitation-based indices is that precipitation deficits are important drivers of drought. They are also easy to understand and easy to compute. Now, as for weaknesses, you do need to have a long data record of at least several decades in order to obtain reliable results. This becomes especially true for flash drought, where rainfall deficits occurring over only a few weeks can be very important drivers of flash drought. Now, other weaknesses are that precipitation indices do not account for changes in evaporative demand, and any impacts on the land surface can only be inferred. So then there are other indices that depict anomalies in atmospheric evaporative demand, which is another important driver of flash drought development. Evaporative demand is also relatively easy to compute. This can be done using either in situ observations or output from land surface models and reanalysis data sets. Now, like precipitation-based indices, however, there are several notable weaknesses when using indices that are based only on evaporative demand. Now, two of the most important weaknesses are that such indices do not account for precipitation, and they do not provide direct evidence of impacts at the land surface. For example, it's very common for periods of elevated evaporative demand across the eastern United States to actually have increased rainfall because the hotter weather leads to more thunderstorms. Now, this means that indices that look only at evaporative demand can actually have extensive areas of false alarm because the elevated evaporative demand may also be accompanied by heavier rainfall. So another class of indicators focuses on soil moisture, which is a very important drought indicator due to its relationship to vegetation health. Notable strengths of soil moisture-based indices are that they provide a measure that is directly relevant to vegetation health. They can also be computed from a variety of sources, such as in situ and remote sensing observations, or from output from land surface models and reanalysis data sets. Now, weaknesses of these indices include the presence of large spatial heterogeneity in soil properties, which means that observations may only be representative of a small area. They also require detailed knowledge about soil types in order to compute the field capacity and wilting point, which are necessary in order to determine if drought conditions are actually occurring. Now, lastly, in situ sensors can be difficult to install. Land surface models can be biased, and satellite retrievals are only sensitive to the uppermost few centimeters of the soil profile. Now, despite these weaknesses, soil moisture is very important for drought monitoring applications. Okay, so the final class of physical indicators I'm going to discuss are those that depict changes in evapotranspiration or in the ratio of the actual to potential ET. Notable strengths of ET-based indicators are that they are a direct measure of vegetation health, with below normal ET strongly correlated to poor vegetation health and to reduced crop yields. ET-based indicators will also respond quickly to rapidly changing conditions and can be computed using remote sensing observations or output from model reanalyses and land surface models. ET-based indicators also have several weaknesses. For example, current versions of satellite-based ET datasets are only available in clear sky areas, which can delay their responsiveness during flash drought. Modeled ET can be heavily parameterized and biased, and in situ flux tower measurements of ET are very limited. Now, despite these limitations, ET-based indicators are very important because they provide direct evidence of drought impacts at the land surface. Now, as such, they have been used pretty extensively. They've been used in many flash drought studies during the past decade. Now, before moving on to discuss some of the challenges and gaps in existing flash drought monitoring methods, I also want to discuss the U.S. Drought Monitor. Now, notable strengths of the Drought Monitor are that it is impact-based and generated at weekly intervals based on expert analysis of multiple data sets and a feedback from observers in the field. This makes it unique among drought indicators because it combines some information from more than one data set. Now, a weakness of the Drought Monitor is that it contains many drought signals because it's designed to depict all types of drought and also contains a subjective component due to human involvement when making the weekly analyses. Now, these aspects then can limit its utility for flash drought monitoring purposes. Okay, so next I want to summarize results from these previous slides, and I'm also discuss some of the challenges that we experience in regard to monitoring the evolution of flash drought. Now, as mentioned earlier, there are many drivers and many impacts during flash drought that together require a large set of tools in order to monitor flash drought from its inception to the end of the rapid intensification period and also beyond that. Now, I want to emphasize again that no single monitoring data set is able to provide a complete representation of flash drought. Instead, it's necessary to use multiple indices that capture different aspects of flash drought. It's also important to use monitoring tools that are able to respond quickly to changing conditions. This sometimes means that you can use existing methods, but only when they are computed over short time intervals appropriate for flash droughts. It's also helpful to use data sets with high spatial resolution so that you can capture local conditions. That typically means using satellite-derived data sets as much as possible because they have very high spatial resolution compared to other data sets. You also need to use data sets with a reasonably long period of record so that you can have a proper understanding of what is normal for a given location and time of the year in order to determine whether or not the rate of intensification that you're seeing is truly more rapid than normal. A final point I want to make here is that in the context of operational applications in drought early warning systems, it's also important to minimize data latency as much as possible because data lags can delay drought mitigation efforts. This is also relevant for the NIDIS drought early warning systems where the spatial and temporal resolutions of those systems need to be increased as much as possible in order to provide early warning of flash drought development. Now, regardless of which data sets are used to monitor flash drought, a key thing is that we need to agree on a general framework for what flash drought is because how we define it impacts how we monitor and forecast them. We also need to better understand where and when each metric is most useful for depicting flash drought. Again, the emphasis here is that we need to use more than one data set to monitor flash drought, but to use them effectively, we also need to know when and where they work best. Now, this takes an honest appraisal of their strengths and weaknesses because there is no single data set that can capture all aspects of flash drought. For example, atmospheric drivers such as precipitation and evaporative demand don't provide any direct evidence about impacts, which are key for drought, but they can provide very useful early warning. A final point is that all studies have focused on soil moisture or vegetation flash drought, but there's no reason why the flash drought terminology can't also be applied to other types of drought, such as hydrological drought. Okay, so I'd like to end with a couple of final thoughts. First, it's critically important to look at changes in the index rather than just the current value of the index, because the key characteristic of flash drought is its rapid rate of intensification. If you only look at the current value of a given index and not at how that variable has been changing with time, then you can't identify flash drought because you're missing the time change component of it. Also, it's important to account not only for the flash part of the definition, but also the drought part, so that you can include the impacts caused by flash drought. Also, finally, I'll reiterate here that like all types of drought, impacts are a key feature of flash drought. which means that flash drought monitors need to include impact-based indices such as soil moisture and ET, in addition to indices that depict the meteorological drivers of flash drought. This framework is consistent with the flash drought definition that was added to the AMS glossary last year. So with that, I'll stop here. Thank you for your attention.
Wonderful. Thank you so much, Jason and Mark, for that presentation. If we can move to the next slide, please. And I invite Jason and Mark, if you'd like to turn your cameras on, that'd be great. If not, that's fine as well. But we have a few minutes here, about 5 minutes, for you to comment and reflect on some of these themes that have come up the previous few days. Which one of you would like to go first?
Go ahead, Jason. You're hot. You're on a roll.
All right. Yeah, we've had a lot of very interesting, very useful discussions this week. I thank Molly for putting together this slide at 11 o'clock last night, she said, so thank you, Molly. I think, there's been a few themes that have come out this week. One is from a monitoring perspective, do we focus on rapid onset versus rapid intensification? Can a flash drought occur within a longer term drought? And does this distinction matter? I would argue that it does not, because rapid intensification can apply to rapid onset or to rapid intensification during existing drought. But that's just my opinion. There's also a need to identify key indicators for flash drought. So is it important to be able to remove other signals from the data sets? Because the reality of it is since flash droughts are a subset of all types of droughts, most monitoring tools are also designed to detect other types of drought. So you have to have some kind of expert guidance or understanding in regard to how to interpret signals within those monitoring data sets. A third point that's come up a few different times is, who is the audience that we're actually targeting when we're defining flash drought? This is, it kind of blurs the lines between research and just the general community, because flash droughts definitely capture the attention of people outside of research, but yet the researchers really need to define what flash drought is, and then it kind of becomes the next step is trying to make sure that message is delivered to everybody else, that that we think that this is what flash drought should be, but then there's always still room to to tweak that definition. As for a research need, like I was mentioning in the last few slides of the presentation, there's definitely a need to better understand the compound and cascading impacts of flash drought, because just to reiterate again, you really can't capture their evolution with just one data set. You really have to look at a sequence of data sets, because that captures how they compound and cascade with time. So definitely have to work on that too. Do you have any other follow-on comments on Mark?
I think you've covered it really well. I'll just make one additional comment. And I think there's already some good conversation going on in the chat box as well. I think you made a key important point that I've heard come throughout this week so far is we have to know what it is if we're going to monitor it, and to eventually hopefully forecast and predict it, right? So I think if one thing can come out of all this effort eventually, it's going to be what's the metrics that we use to do just that, so that we're on the relative same page in both monitoring and forecasting this phenomena, because I think it's critically important going forward. So I look forward to some of that conversation in the breakouts.
Wonderful. Thanks to both of you. In the interest of time, I think if you do have questions for Jason or Mark, please go ahead and use the chat box to type those questions, and they'll be monitoring that to respond. But thank you both so much for that great presentation and those thoughts. So thank you. Okay, we are going to move on now to the prediction presentation, which will be given by Andy Hoyle and Hylan Wong. So go ahead and move to the next slide. Thank you.
Good morning, everyone. I'm Andy Hoyle of the NOAA Physical Sciences Laboratory, and with my colleague Hyland Wang of the NOAA Climate Prediction Center, we will overview challenges, gaps, needs, and opportunities of flash drought prediction. In the first half of the presentation, I will discuss challenges and gaps. In the second half of the presentation, Hyland will discuss needs and opportunities. We use three themes to describe challenges, gaps, and needs of flash drought prediction. The three themes are operational forecasts, the tools or initialized prediction systems used to make operational forecasts, and prediction skill and predictability of environmental conditions related to flash drought. For operational forecasts, we note that flash drought forecasts are in their infancy, and this forces stakeholders to use operational forecasts that were not specifically designed for flash drought, and that existing operational drought outlooks are not consistently skillful. The Climate Prediction Center's monthly drought outlook is the operational forecast product that best applies to flash drought. The monthly drought outlook is released once each month and predicts drought development over the subsequent 4 weeks. The monthly drought outlook was created in response to the Central United States flash drought of 2012 and went into operation in the summer of 2013. The monthly drought outlook failed to forecast the 2017 Northern Great Plains flash drought. We illustrate this point using the latest U.S. Drought Monitor release in May, June, and July of 2017, and the monthly drought outlook valid at those times. The monthly drought outlooks in May and June of 2017 did not forecast drought development that was observed over Montana, North Dakota, and South Dakota. More generally, when accounting for the performance of the monthly drought outlook during 2013 to 2019, we find that it was not consistently skillful. This is illustrated using the time series of monthly drought outlook verification provided by the Climate Prediction Center. Skill is defined as the difference between the fraction of correct forecasts of drought improvement, removal, persistence, and development using the U.S. Drought Monitor as truth, and a persistence forecast baseline. Skill is computed for the entire United States. The maximum possible score is 100, and the minimum possible score is -100. As the time series indicates, the skill of the monthly drought outlook is variable. The highest skill forecasts were issued in 2017, but in recent years, there have been many low skill forecasts. We now turn our attention to forecast tools. Many prediction systems used today are inadequate for guiding skillful and detailed flash drought forecasts for two reasons. First, they are infrequent, untimely, and their resolutions may be too coarse. And second, they lack the breadth of variables relevant to flash drought. We used the Northern Great Plains flash drought in 2017 to illustrate the limitations of flash drought forecast tools. The left-hand portion of the slide describes the rapid onset of the drought at Glasgow in northeastern Montana in May, June, and July of 2017. Soil moisture percentiles from the UCLA Surface Water Monitor, shown in the top row, indicates a standardized soil moisture decline from the 70th percentile to the 10th percentile between mid-May and mid-June. The rapid land surface drying was related to the failure of precipitation from mid-May to mid-July, on average the wettest time of year in Glasgow, and above average temperatures. The right-hand panel shows the cumulative precipitation anomaly from May to July 2017 at Glasgow and observations, as indicated by the black line, and for sequences of global forecast system predictions at various lead times, the red and blue lines. Reconstructing a forecast based on various lead times allows one to assess how far in advance an observed outcome could have been predicted. Comparing the forecast precipitation accumulation with the observed precipitation accumulation in Glasgow, we find that sequences of longer than 3-day lead predictions did not capture the evolution of precipitation anomalies during the spring and summer of 2017. This result, along with predictions from the North American Multi-Model Ensemble made in advance of the season, strongly suggests that this drought was unpredictable in the generation of models available in 2017. The forecasting community has more tools than ever before, but despite consistent improvements to established efforts like the North American Multi-Model Ensemble, in the emergence of new programs like the Subseasonal Experiment, also known as SubX, the tools remain inadequate for flash drought prediction. We use Table 1 from the publication describing SubX by Pigeon and colleagues to illustrate this point. At the time of publication in 2019, SubX was comprised of 7 models, all of which follow different protocols. Predictions were made available for each model on different days of the week, and the forecast ensemble size for each model was different. Moreover, all forecast data was available at common horizontal resolutions, which may be too coarse for flash drought predictions. Finally, we turn our attention to prediction skill and predictability. Currently, there are only a few known sources of predictability. These sources include Rossby waves in the atmosphere that originate from distant locations and the initial state of the land surface. Also, models are imperfect and many lack skill, and the multifaceted nature of flash drought requires that many variables, and not just a single variable, be forecast accurately. In a perfect world, every drought has a systematic cause that can be predicted, but in reality, we know of just a few systematic causes, and we have found that only a few models can predict them. Also, the same source of predictability may not apply to each and every drought, so we are constantly searching for new sources of predictability that we may be able to leverage for the skillful prediction of future flash droughts. In the case of the 2012 Central United States flash drought, DeAngelis, Wang, and colleagues found that the origins of the drought could be linked to atmospheric waves, called Rossby waves, originating over Asia. But they also found that few models participating in SubX could forecast this phenomenon. With regard to the 2017 Northern Great Plains flash drought, its predictability sources, if any, remain unknown. My colleague Hailan Wang will now present on the needs and opportunities of flash drought prediction.
This is Hailan Wang from NOAA Climate Prediction Center. We will next discuss the needs and opportunities of flash drought prediction. We will use the same 3 themes as those for challenges and gaps: operational forecasts, forecast tools, and prediction skill and predictability. For operational forecasts, the indices for flash drought are preferably integrative, in order to characterize flash drought as a multivariate and multifaceted phenomena. The indices should use the same as those in the monitoring community for consistency. The flash drought forecast should be probabilistic in order to incorporate the effect of the chaotic nature of the Earth system, particularly that of the atmosphere. The probability information of flash drought forecast is also essential for addressing user needs and facilitating their decision-making. The forecasts need to be issued frequently, ranging from daily to weekly, in order to capture flash drought as a rapid evolving phenomenon. The flash drought forecasts need to be aligned with impacts when possible. Examples of these impacts include those on agriculture, such as soil moisture, evapotranspiration, and vegetation health. NOAA CBC is an operational center to produce and issue forecast products for the public. Currently, it is one of the key tasks at CBC to develop and produce flash drought forecast products. A main goal is to develop experimental probabilistic flash drought forecasts. This work includes the development of flash drought prediction system comprised of dynamical and statistical components. It currently is in its infancy and will take years of research and development to materialize. A flash drought-related product that CBC plans to release next year is an updated U.S. Week 2 Hazards Outlook, in which the Week 2 flash drought forecast will be added. The U.S. Week 2 Hazards Outlook is released every weekday and targets a Week 2 forecast period. It currently includes precipitation, temperature, snow, and wind. The product uses a probabilistic and categorical format. They're produced by subjectively integrating objective inputs, one of which are dynamical model forecast ensembles. CBC is currently working on adding Week 2 flash drought forecast to the map and expects to release a new product next year. Finalizing this new operational product has several requirements. They include discussions with both CBC Drought Outlook and U.S. Hazards Outlook forecasters, coordination with the NWS Regional Operational Center staff, climate service program managers from that region, and when and where available, contacts from CBC's core deep relationship partners such as USDA. Next, we turn our attention to forecast tools. As Andy has pointed out, many of the current prediction systems are inadequate for guiding skillful and detailed flash drought forecasts. The forecasts they produce are infrequent, untimely, of coarse resolution, and lack the variables that are necessary to produce flash drought forecasts. Therefore, dynamical model forecasts need to use improved protocols. Our recommendations include consistent initialization dates, more frequent forecasts, higher spatial resolution, make more variables available in the forecast output, produce more ensemble members. The production of multi-model-based operational forecasts also requires statistical post-processing to improve the skill and probability of the dynamical forecast. This includes bias correction, calibration, and consolidation. Further, multiple land surface models are required to produce high-resolution hydrological forecasts. These land surface models will be forced with the bias-corrected and calibrated meteorological forecasts. In addition, statistical prediction models should also be considered. They can potentially add skill for regions and seasons that dynamical models show little prediction skill for flash drought. They can also help assess flash drought predictability. Finally, we turn our attention to prediction skill and predictability. Exploratory research is required to identify new sources of flash drought predictability. For those identified predictability sources, research is required to assess how well these sources and their effect on flash drought involvement are represented in current and future generations of forecast models. The investigation can also help diagnose sources of model biases related to flash drought processes and inform model development. In addition, climate has been changing. It is necessary to perform research to better understand the effect of climate variability and change on flash drought prediction. Considering the data and tools that are used to produce flash drought forecasts, the dynamical models and forecast systems need to be further improved by reducing model biases and developing more advanced forecast strategies. Flash drought forecasts should also leverage advancements made in monitoring, particularly for early warning indicators such as changes in evapotranspiration. Lastly, flash drought prediction should incorporate developments in statistical models by, for example, taking advantage of recent advancement in machine learning approaches. These statistical models can potentially complement dynamical models and add skills for regions and seasons that dynamical forecasts are of limited value. This ends our presentation on flash drought prediction. Thanks for listening.
Great. Thank you so much to Andy and Hyland for that great presentation. If we can move to the next slide, I'll invite Andy and Hyland to provide some reflections so far on some of these topics that have come up. And please feel free to turn on your camera if you would like. We just have a couple of minutes for your reflections. So Hyland, would you like to go ahead? Oh, I think you might be muted. Oops. I'm not able to hear you. Andy, do you want to go ahead and then we can hopefully get sound for Hyland?
Yeah, it could be a GoToMeeting issue. Yeah, I'll begin with predictability limits. And we talk a lot about this in the research community about where are those predictability limits right now? And can we introduce new physics, new tools, new models, new understanding to be able to push those predictability limits back? And the work that we're doing and will continue to do within the community, we'll be able to figure that out a little bit more. And as I kind of reflect on the chat box, folks are asking questions about, well, why aren't you looking beyond 2 weeks or 3 weeks or 4 weeks? And the issue there is sort of where we're at in the way we perceive weather and climate. Where is that bridge between the two? What is weather, what's climate, and what can we predict with any sort of skill in the midst of that? And I think that all comes into the limits of predictability and what are they, where are they, and how do we push them back? And hopefully Hyland's sound is back because I'm about to hand it back over to her.
All right. Yes, as Andy just mentioned, based on the current operation forecast system, the picture we have isn't great because currently the prediction scale of flash drought, for example, in terms of the precipitation temperature anomaly associated with the flash drought, is typically limited to 2 weeks or 3 weeks at most, kind of depend on the specific event and specific forecast system we look at. Just mainly because the sources of flash drought predictability that have been identified so far are kind of limited. And on top of that, the operational forecast systems have substantial biases, and these biases further limit the leverage of these limited sources of flash drought predictability, and just contributing to this limited prediction scale. But if we look forward to the future, my suggestion is that we need to use an open mind. We shouldn't be discouraged by the current limited prediction scale, because we may expect to see improved prediction scale as the future research reveals new sources of flash drought predictability. For example, if we have new flash drought events occurring with new features, and also we expect the forecast system to be much improved in the years to come. And another thing we want to mention is the two needs at CBC. I can provide more details at discussion this afternoon. Currently at CBC, it's a key task to develop the flash drought prediction products in order to address user needs. And one of the tools we need are advanced land surface models, preferably high resolution and with dynamic vegetation. So we're looking for opportunities for the external collaboration to transition land surface model to CBC.
Great. Thank you so much to both of you. And we will move on now to our final presentation on planning for flash drought and response. And we have a presentation from Tim Hall, who's with Iowa DNR. If you can move to the next slide for the presentation.
Hi, my name is Tim Hall, and I serve as the Hydrology Resources Coordinator for the Iowa Department of Natural Resources. And I'm going to provide you some of our thoughts and comments about flash drought from the state of Iowa's perspective. We in the DNR, as just a quick introduction, we provide services both on the conservation and recreation side and the environmental side for the DNR. In our state, those two agencies are one and the same. We have an environmental services division, which does air quality, land quality, water quality, all of the permitting and compliance, along with conservation and recreation that does hunting and fishing and forestry and state parks. So we're all in one agency together, and those different staff can come together when dealing with drought issues. Just a little introduction, Iowa DNR drought work. In 2011 and into 2012, we started to discuss the drought that seemed to be looming. And as a result of that, we had a lot of multi-agency and multidiscipline discussions. Emergency management folks, our partners at the Department of Agriculture, which includes the state climatologist, the U.S. and Iowa Geological Surveys. We had conversations with a lot of commodity groups, corn growers, the Soybean Association, pork and beef, commodity groups, as well as water system managers. We have rural water systems in parts of the state that serve large areas of the rural communities. We looked at those meetings as important because they laid the groundwork for long-term collaboration between partners. When we got to the point after 2012 when we needed to have discussions about drought, we had some pre-established relationships that we could build off of, and expanded the understanding of a lot of state partners related to drought issues, and also led to the development of what we call the Water Summary Update, which is a monthly publication. And I'm going to share a little bit about that because it impacts how we communicate drought issues in the state. We did build some long-term collaboration through our meetings, though. We got hydrologists, geologists, we got agronomy folks, crop folks, policy staff within the governor's office and other agencies talking about drought and drought issues. We also were able to make inroads in establishing relationships with other state and local and federal agencies, a lot of our university partners, and also some state legislative officials and staff, which again is useful when you're trying to build on some long-term working relationships. We also expanded what we understood about drought. We had a lot of program staff. They were able to cross-train on drought issues. So some of our water supply people that were less familiar with drought and drought-related issues were able to learn quite a bit. We've had formal presentations over the past any number of years from the National Drought Mitigation Center folks who've been kind enough to come over to Des Moines from Lincoln. U.S. Geological Survey and National Weather Service folks have come and made presentations to the DNR staff. We've been involved in a lot of university studies related to drought and water resources. We've been able to build some knowledge base in other state agencies as well. And it's also provided us an opportunity to get acclimated, pardon the pun, to climate and weather data from other agencies that normally we don't touch. So it's been good in that regard to make us better understanding of drought issues. We developed a water summary update. It started in the spring of 2012, a collaborative effort, kind of an outgrowth of some of those discussions I was just mentioning between primarily the DNR, the state climatologist, U.S. Geological Survey, and the Iowa Geological Survey. We intended the water summary update to be a snapshot of hydrological conditions. We cover precipitation and temperature, stream flow, groundwater, and the U.S. Drought Monitor. We continue to this day to reach a broad general audience. We get local interest from news media, radio stations, newspapers. It still has a fairly broad audience right now. And just quickly, the water summary update, we provide figures like these. We provide precipitation and temperature information. There's some groundwater resource information and some general stream flow. You'll note that there's no more than 2 pages of text with this document, so it's a fairly brief and concise document. It's our primary tool for communicating drought issues to the general public and also to other agencies. It's great for engaging policymakers because it is pretty broad. And it provides basic information. Sometimes we would like to put additional information in there, but we're sensitive to the fact that it's not a technical document. And we have so far not focused really any attention on flash drought. We've just been dealing with drought in its general sense. So why is this important to us? Well, the 2019 to 2020 flip-flop helps to point out the need for attention to some of these flash drought issues. This is a figure that shows basically the early part of 2019, January through October, the first 10 months of the year. And you'll see that this part of this, all the state, and particularly this part of the state, we're in the top 10 wettest years in 2019. This is the exact same area in time, but just advanced 1 year. This is January to October 2020. So we went from a top 10 wettest 10 months to now 4th, 6th, and 8th driest. That quick flip-flop has provided us an opportunity to explore some of these issues with our partners. So we went from the top 10 wettest to the top 10 driest years, especially in the western third of the state. Just a couple of observations. Iowa is dominated by agricultural concerns. So growing season and soil moisture issues are of considerable interest. There are some parts of the state where water supplies are more vulnerable to drought, including flash drought, particularly in northwest Iowa, which is one of the areas that showed up on those maps just a moment ago. It's dominated by beef, dairy, poultry, egg, pork production. There's a growing sensitivity to water resource issues, particularly after this year. There's been some attention paid to drought issues, and I think we're turning the corner on some sensitivity in that part of the state. Now I want to turn to the focus of this discussion, what would be helpful to us in terms of research needs, monitoring, prediction, planning, and response. And I'm going to add one more to the list, and that's communication tools and experiences. And I'll get to that in just a moment. As I think about what would help us in terms of research needs, small stream response to flash drought. We get a lot of questions about when will we know we're out of a drought. If there's anything we could do to help us understand ways to flag getting into versus getting out of a drought, especially flash drought, that would be helpful to us. Also, thinking about time-based impacts, is there a way to provide some sort of visual prediction of potential impacts over the next month, 2 months growing season? And in a flash drought, is there a way that we can help to communicate the short-term impacts or potential impacts of drought conditions? In terms of monitoring, we always would welcome more soil moisture data. We're starting to develop a system of soil moisture gauges in the state, but it's still challenging to pull moisture out of those. Stream flow monitoring is important to us, especially small streams, ungauged streams. If you look at the state of Iowa, here are all the USGS gauging stations, and there are some significant parts of the state, again, that western third, where we just don't have a good handle on small streams, and we struggle sometimes to understand what's going on with stream flow. So that would be useful to us. In terms of the prediction side, are there statewide triggers that can help us know if we're in a flash drought or we're moving into a flash drought? I realize flash drought by its definition happens quickly, but is there a way that we can get a better handle on whether we are moving into a flash drought? And then is there a way that we can divide impact sectors? The Department of Agriculture looks at agricultural impacts. We tend to look at water supply impacts. Is there a way that we can develop predictions and projections specific to those sectors? Planning and response. We are starting discussions in the state of Iowa to develop a statewide drought preparedness plan. And when we are able to get that moving, perhaps in 2021, we would want to look to provide provisions for flash drought planning in there. Continued assessment of the results of the 2020 drought conditions would be helpful as we develop and find data and information to help us understand exactly what the impacts were. Response to drought needs need to be continually assessed. We need to stay on top of the response numbers and data and information. And there's always the need to balance statewide efforts with local or industry segment-led efforts. We at the DNR tend to be more of a facilitator of information that we try to get disseminated to local or industry folks on drought issues. This is the one that I added to the list back on the earlier slide. Communication tools or experiences. Much of the DNR's role has been to sort of review and assess the technical issues, the technical data that's out there, find the information that is important, and then figure out how to communicate that information to a fairly broad audience. Our target audience is not technical. We do reach some industry and technical people, but our role is more to pull the technical information in, package it up, and figure out how we can disseminate it to commodity groups, water system operators, county emergency managers, local politicians, local news media. Early on in the water summary update, there was a discussion about whether we should make it a technical document or a general outreach document, and we went down the road of general outreach. So what I am getting at here is that the ability to tap into what other folks have done for communication tools and experiences would be helpful to us. How have other folks been able to communicate flash drought issues to a broad audience? And anything we could do in that regard would help us practice this principle of R&D, which I call a rip-off and duplication. I would love to take ideas that work in other places and bring them over to the state of Iowa and figure out how we can duplicate them in how we function in our efforts. So communication tools, what works well, what experiences have worked well. If we could learn the things that have not worked well for communication issues, That would help us also to not repeat the errors of other folks. With that, that's just sort of my brief overview, hopefully hitting the points that folks would be interested in. This is my contact information if you want to give me a call or drop me an email. If you want to look at the water summary updates, you can go to iowadnr.gov, and there's a little search box and type in water summary update, and you can access all of the water summary updates. I think we're on number 112, so you can go back and see the history of how that's developed over time. But that's what I wanted to present, and I will be happy to answer questions or help provide clarification. Thank you.
Thank you, Tim. If you'd like to move to the next slide, we will have Tim provide a few comments on what we've heard so far at the workshop.
Thanks, Molly. I know we're up against the scheduled deadline, so I'll be very brief. As you can tell by the presentation, I am not a researcher, so I kind of feel a little bit out of place in this group because you all are on the research end of things, and I'm clearly not. But I do appreciate the chance to provide a rebuttal to myself, which you don't get to do very often. You know, much of the emphasis of what I do is taking what I hear here from you all and figuring out how it applies to industry folks and helping them understand the necessity to develop some response activities to flash drought. So this idea of rapid intensification, which I hadn't really thought too much about before this conference, really resonates because oftentimes when we talk to, say, an industry that's a heavy groundwater user or heavy surface water user, getting them to understand the nature of the potential threat to what they do in the context of rapid intensification is important. So thinking about how there could be a metric or a way to communicate that. Much of what I do is communication. It's how do I communicate a potential risk to someone who might be threatened by that risk. So what's happening in the research community is important. I see my role as sort of standing in the middle between you all on the research end and then the end users, the water users on the other side in the state of Iowa, and how do I get the right information and communicate it in a way that's understandable to people on the other side is my role. So a lot of what's happening here is great for me to know. My role is going to be how do I turn it around and communicate it in a very simplified but effective way to users. So that's kind of the gist of what I wanted to talk about, and I'll leave the rest for discussions in the smaller groups if that's appropriate, Molly.
Yeah, that sounds great. We will have some time to discuss in the small groups, and then also later this afternoon after we have our report outs from those, we'll have some discussion. Thank you again so much to all of the presenters for those great comments to sort of get us queued up for moving into the breakouts. If you could move to the next slide, please. So we are moving into our third and final breakout session, which is focused on this theme of the opportunities, gaps, and needs related to monitoring, prediction, and planning and response. We'll have 45-minute discussions again in 8 different breakout groups. And we do have these organized by topic. And so you can find the group that you are in on the agenda or by your calendar invitation. Marina is starting to put the links into the chat box. You can also find the Google Meet links either in your calendar invitation or on the agenda. Next slide. So just a brief overview of what we'll be discussing. You know, the presentations really queued us up to start talking more about the gaps and needs, reflecting on what you heard, and then also adding in your own thoughts. So for each topic, you'll focus on just one topic in your breakout group. We'll look at the gaps and needs in research in the topic area. What tools do you think would create the most value for users based on what you've heard at the workshop so far? And then what are some current activities that could be leveraged to really help us meet these researcher tool needs? Because we obviously want to take advantage of what's already going on. So at this point, we have just a quick 5-minute break. We are going to be starting our breakout groups in about 5 minutes at 12 Eastern, 11 Central, 10 Mountain. I'll let you guys do the conversions. But go ahead after you leave this room and have your break, just go straight to the Google Meet link for your breakout group. And if you have any issues or questions, we are going to leave the GoToMeeting open if you need some help with that. But we will see you all in the breakout groups in 5 minutes. And then also just a quick note after that, we do have lunch and then we will go into our report out. So we will return in the larger group in about an hour and a half. We'll see you in 5 minutes. Thanks, everyone.